Okay, in this video, functions of real numbers. Now we're finally going to get into it. This video corresponds to section 1.1 in Stewart, 4 ways to represent a function. I'm not going to write that whole thing down, but our objective in this video is to define real valued functions. And I'll get into, again, what all this means of a real variable. And we'll express them in multiple ways, hence the title of the section, 4 ways to represent a function. So first of all, in order to really talk about these functions that we're going to be working with intensely in this course, we need to talk about the real numbers. And more or less, all this chapter is going to be, in some sense, review. But our top level view here is that we're talking about all numbers with decimal representation that fit on the real number line. And we typically denote this as the set negative infinity to infinity with parentheses, or we can call this blackboard R. Blackboard in this case meaning that there's a double line where the vertical bar for R is. And this is usually where we start in algebra with our discussion of numbers and what number is. So the real number line, we typically represent it as a horizontal line that extends out, where we imagine it extends out forever in either direction, left or right. And we put these hash marks, and usually we just represent the integers here, so counting numbers, their positive and negative counterparts. But we obviously are talking about including such things as these numbers, as well as something like 1/2, perhaps even somewhere in here is the Euler's number E, which is an irrational number. Pi, square root of 2, 1.00000005. These are all real numbers. So how do we classify them, right? So the real numbers are built up, and the way that we want to imagine them is using this classification scheme, where we're talking first about the natural numbers, so 1, 2, 3, and so on. And this really is just a microcosm of what comes next, which is the integers, which is denoted as blackboard Z. So natural numbers, blackboard N, blackboard Z for integers. It's because it comes from a German word. And the integers include such things as negative numbers, 0, and the natural numbers. So I'm not skipping -1, by the way, in what I wrote here. I would just, for the sake of clarity. Then we have blackboard Q, which represents the rational numbers. Rational numbers are fractions. We're talking about 1/2, 33/34, and so on. Anything that can be represented as a ratio of 2 natural numbers or integers. Lastly, the final step here is including things that are not rational. And when we include things that are not rational, we have the real numbers. So this is, you want to imagine this as a nesting set, right? Like Russian dolls. So real numbers include rational numbers, which include integers, which include natural numbers, but not necessarily the other way. So now we introduce things such as the rational numbers and the irrationals. And we'll talk about some very interesting consequences of that in much later videos. Right, so what can we do with real numbers? There's all the typical sorts of things. So operations on real numbers include such things like your standard addition, subtraction, multiplication, division, except by 0. Can't divide by 0. So these are the binary operations. And we've also got some other interesting operations, such as exponentiation, right? So x raised to the n power, for instance, that's exponentiation. But you also have roots, so the nth root of something, and absolute value. So these might also be called unary operations. These words represent what things are involved in the operations. For binary operations, we have two real numbers that we're combining in some way. And the unary operations just rely on one real number that we involve. In other words, this encompasses all the algebraic operations that we are used to and that we've discussed from grade school up until this point. Lastly, before we move on, we should talk about interval notation, because it'll be easier to talk about certain sets in the real number line. So on the real number line, we may be interested in talking about just one short segment. So for instance, here's 1/3. And let's suppose we're interested in talking about this subset, which we might traditionally write as the set of all real numbers, such that x is greater than or equal to 1/3. Hence, closed circle. Whoops. Closed circle means includes, so it can be equal to 1/3, but not necessarily. I do want to make a note here because this is a symbol I'm going to write fairly often. This means belongs to or is an element of. It just means x is a real number. But interval notation is a lot more compact, and so instead we can write this set as bracket 1/3, comma, to infinity. Okay, so we're representing this ray, so it's an infinite set. It's not the whole real number line, but this is the interval notation, and so what we can use this for is for things like rays and intervals. This is an example of a ray. So rays typically are things like negative infinity to b being some number like 0 or 5 or whatever, or negative infinity to b including that real number. Or we can be talking about a to infinity not including a, or a to infinity including a, which would mean we need to make that a bracket. So rays extend out infinitely in one direction. Intervals, on the other hand, look like they have two endpoints, okay? So I'll draw an example in a second, but the inclusion of the endpoints doesn't necessarily matter. All we care about, usually, is where it stops and where it begins. So here's the real number line again. And let's say we're talking about the interval -1 to 2/3. And we're going to include 2/3, but not -1. And so we might represent that in interval notation as parentheses -1, comma, 2/3 bracket. And that represents that interval that starts at -1, but don't include -1, and up to and including 2/3. All right, this should all be review. If it's not an issue. Please do make a note here, if this is something that you're unfamiliar with, that you should then work on interval notation, or you should work on understanding the real numbers. All right. But, all right, let's get into the main event, which here is defining real valued functions of a real variable. And it's kind of a wordy definition. The name is not, it doesn't roll off the tongue very nicely. So usually, or rather I should say almost always from here on out, we're going to skip the formal definition, the formal name of the word, and we're just going to say functions. Right. So let's define them. What is a function? So definition. A function, which we denote as lowercase f, sometimes we say math text f, or script f, colon, a right arrow b, is a relation. And a relation is another precise mathematical word, but we just mean we're relating things in A to B, such that for each element in A, we assign f of x in B. So that assignment there is what we're saying is everything in A, so A being a set, it can be the real numbers, it can be a subset of the real numbers, and similarly for B. But for everything in the first set, we assign it some other number in B, okay? And so these are all real numbers. We're only talking about real numbers here, okay? So let's see an example here. Example. So, what is a function? Something like the relation y equals x squared is a function. Why is it a function? Because we're saying every x gets assigned a y. And that y is unambiguous. We're just saying take that real number and square it. So raise it to the power of 2. So that is a function. On the other hand, x equals y squared is not. And in this case, remember, what we're saying is we're agreeing that y equals f of x is a shorthand that allows us to not have to say f of x all the time. But in this case, x equals y squared is not a function. For reasons that'll be more clear later, but in short, we don't get a single y from every x. We may actually get multiple. And so this makes it not well defined. And that's a word that so we might say this is ill-defined or not well defined. And for this, then we say this is not a function. It's a relationship, but it's not a function. So a note about notation. Our formal notation for functions is, so formal would be f colon a to b, a and b being sets, as f of x equals y. So there's some rule that we define for this function. The shorthand is we just say y equals f of x. So we skip the whole f of x equals y as, there's usually no need for that, okay? So let's think about how to represent functions. Representing functions. So our first technique that we'll use is visually. And by visually, we actually mean a couple of different ways. So the first that we might encounter is what we call an arrow diagram. So we imagine these two sets, A and B, They're sets of numbers. And f is an arrow that points from A to B. So we take some element in A, and what f does is it assigns it some element in B, like that. So, for example, let's say we have the function f taking the set 1, 2, and 3 and assigning -1, 0, and 1 specifically in that order, right? So we have the set A like this, 1, 2, and 3. Now we have set B like this, -1, 0, and 1. And what f is it's this green arrow that's assigning to each element in A something in B. So if we're tracing each arrow, what we're saying is f of 1 equals -1, f of 2 equals 0, and f of 3 equals 1. So we're making that assignment from things in A to things in B. The more useful way that we'll represent functions visually is using a graph in the coordinate plane. So, to refresh your memory, what we're talking about here is the coordinate plane being two perpendicular axes, horizontal one being the x-axis, and the vertical one being the y-axis. And every point x comma y is represented in terms of distance from the origin. So here's 1, here's 2, here's 3. This is distance along the x-axis and distance along the y-axis. And so, if we have as an example, the function y equals 2x minus 3, then what we're saying is we're going to represent all the solutions of this equation, y equals 2x minus 3, on the coordinate plane, and hopefully it's an unbroken line or curve or some set that makes sense here. So, for instance, we know that the point 0, 3 is a point on that line, as well as 1, -1, and 2, 1, and so on and so forth. So this is an example of being able to graph a linear equation, but then this graph represents this function as a set in the coordinate plane. So an infinitely fine string of points that satisfy this equation. The other ways that we represent these functions, so for instance, numerically, that typically means as a table of values. So we'll represent in one column or in one row the x-coordinates and the y-coordinates, or the inputs and the outputs. So that's a very useful way of thinking about this. So input and an output. And if we're talking about more physical manifestations of functions, then this definitely tracks. So as an example, we may have the table of values 0.1, 0.2, 0.3, 0.4, and 0.5 as the x values, and 1.1005, 1.221, 1.350, 1.492, and 1.649, where each y sub I is obtained from x sub I by raising e, Euler's number, to the x sub I power. So, for each I indexed in the table. Now, we'll typically skip the subscript notation, but do be aware that as we move forward, this will come up from time to time, especially as we get into chapter 5. So we'll definitely start talking about indexing our inputs. But so then this represents our function as a table of values where we understand, okay, what is f of 0.3? What we're asking for here is, given 0.3 is our x value, what's the corresponding y value? And our answer is 1.350. We'll be using numerical representations sparsely, but they can be very, very insightful when we're not entirely sure what the behavior of a function is. Third, we may represent a function orally, so description in words. There are some pretty classic examples here, such as when you're discussing physical models. So for instance, a good example might be when you're describing a function volume as a function of radius of a cylindrical solid with fixed height h. And let me just visualize this for a second, because orally is helpful, but oftentimes we put things together as well in order to really represent things effectively. So you might imagine then that this is the cylindrical solid with a fixed height. So here's h. And as a function of radius, means that as we change the radius, the corresponding volume, all the stuff inside the cylindrical solid will depend on r. So v as a function of r, and whatever that might be. But we're representing it orally as this. And then there's also some functions that have special names. For instance, the function, what we call the square root function, is called the principal square root function. And there's a whole coterie of these functions that have specific names. We'll encounter quite a few of them in this class, such as absolute value, ceiling function, etc. The last way that we represent functions is algebraically. So this is the format that we will almost always be using in this course. Of course, we'll use all of them in tandem, but algebraically is particularly helpful because then we get to use other bodies of knowledge of math. So we use, typically, the y equals f of x format. But there are other ways, and I'll get into them in a second. So our first example is y equals x squared minus 1 over x squared plus 1. So all the things that we have discussed so far apply here, where we can understand this as assignment of an input x to an output y. This also gives us, so we can have an arrow diagram if we wanted, or we can obtain a curve in the coordinate plane, or we can obtain a table of values, or oral description, once we understand what the function actually is doing. Our second format, and this is, of course, interchangeable, we may represent things as x gets mapped to f of x. So that symbol right here is mapped to. In other words, what is the input getting assigned to? And so as an example, we might say, when we consider the function x being mapped to the tangent of x, assuming certain things about x, but we'll get into that in a later video. So what we're saying is the function itself is, so interchangeably, we're saying f of x equals the tangent of x. And of course, tangent, spelled tangent function, is also a special name. All right, so those are all the ways of representing a function. In the videos that come, we'll discuss more about functions in much more detail, including their properties, how to find their domain and range, and special families of functions.